Let's now discuss the sort of basic information retrieval view of search, which is Boolean and the vector space model. So, Boolean search is what you always think about of search when you have these. There's still many systems which use this method, which they really shouldn't. I mean, I'm very frustrated with a system called Manuscript Central, which manages journals. It is ridiculous. It uses Boolean search for things which should be free text search. It's really antiquated conceptually. Unfortunately, the dominant system in the journal management area is disgraceful. It really is pathetic. Because it's so obvious what we have to do. We need to do full text search. Ah, anyway, Boolean search is typical, nice logic, lots of logic, and ors, and the terms of these elegant, elegant, clean English words which you divide the document and the query into. And then you just look at these queries such as get Fred and Agatha or Hilda, and then you find all the documents which satisfy that. And you make this very fast by forming inverted indices, which you look at document 1 and find that Fred and Agatha are mentioned, document 2 and as Agatha, and document 3 as Fred and Hilda, and then the inverted index is Fred maps to document 1 and 3, Agatha to 1 and 2, and Hilda to 3. And then when you use that inverted index for the query at the top of Fred and Agatha or Hilda, you will find that it's document 1 and 3 satisfied because they both have Fred and one of them has Agatha and the other one has Hilda. A disadvantage of the Boolean query, it gives no ranking, just a yes-no answer. You can convert the basic idea to give a ranking by making everything rather fuzzy, and there's a whole theory of fuzzy indices which uses one concept it uses is called Jacquard index, which is based on the number of documents. If you take two terms, it's the number of documents containing both terms, or the number of documents containing either one of them. And if this number is large, then it means they're highly correlated. And using this type of concept, you can actually associate a term with a document where the term does not appear, because maybe the document has, if T is the term and JTU is large, maybe U is in the document. So you actually use this to associate a term with documents where it doesn't actually appear, but the related terms appear. So this allows you to get a richer set of responses and also give a ranking, which you must have a ranking, because otherwise you take your million documents to satisfy your query and you have no idea which order to return them. So we've already seen in discussing recommender systems that intuition and technology can be helped by considering funny spaces. And those were the spaces of items and users for recommender systems. Here is the space of words. And it was introduced by Sultan in 1975 for information retrieval. The key thing which is used here is the term frequency. It's a function of document and term. Term is the thing that's a million for English, which are the set of words in the language, the vocabulary. D is the documents. Then TF of D and T says that document D has the term T, TF times in its document. So then the document D becomes a vector, and that vector is just has components which are TF of T for term T, and here I've just listed 3 terms. Most entries in this vector are of course 0. And then we need to decide what nearness means in this context, and we can do that with a distance function, or also there are, just as we saw for recommender systems, there are other ways of specifying it. One of the simplest definitions of nearness is actually used in libraries, where they use classification schemes, because libraries actually have to map documents to a one-dimensional world, because effectively, well, maybe 2-dimensional. You could say the stacks in a library, well, maybe 3. You have height and you have X and Y. So in 3 dimensions, you have to map documents to a position in 3-dimensional space. Here is a nifty library, the so-called Wren Library, which is where I used to study when I was a child, was undergraduate and graduate student at Trinity College, Cambridge. And those stacks are, of course, full of books, which I used to study. Because when I did mathematics, most of the stuff I studied was hadn't been changed since 1850, so the Wren Library was full of useful things for me. Actually, useful for things for me as a student, not useful things for me to learn. Anyway, we have two documents D. We're not going to, we actually don't have them in 3 dimensions. We have them in a million dimensions. And we look at the cosine similarity, which is the scalar product divided by the length of D and the length of E. And the length, of course, is the square root of these components DIs. Each of those DIs is the TF. And we have a similar thing for E. That's slightly, I mean, you have to do something about the length because these documents vary drastically in length. And sometimes this may not be quite the right thing to do because long documents might be favored. But still, this normalizing out is basically the correct thing to do.